Good morning, everyone. I'm Krishna Kumar, and today I'll be presenting our work titled HybriDTVis 3D Building, Road Reconstruction, and Visualization of Hybrid Primitives of City Scale LiDAR Point Clouds for Digital Twins. This is a joint work with Archis Kulkarni and Professor Sreevalsan-Nair from GVCL at IIIT Bangalore. I'll start with the problem context, the motivation, and a brief look at the key challenges. Then I'll walk through our methodology covering road reconstruction, LOD1 building reconstruction, and hybrid rendering. Here, by LOD1, we specifically refer to LOD 1.0, simple keyboard representations, and we don't go beyond that level of detail in this work. Then finally, I'll close with our results, findings, and limitations. Let's start by covering the basics. LiDAR stands for light detection and ranging. The output is point clouds, where each point has 3D coordinates, which we could represent using P, along with other scalar fields such as intensity, number of returns, RGB information, etc. And compared to 2D vision based techniques, LiDAR provides greater accuracy and precision. Then digital twins, that are virtual replicas of physical environments or entities. And in the context of large scale cities, we refer to them as semantic 3D city models. These models combine both geometry and semantics in structured representations. Among all urban elements, buildings and roads are the most fundamental entities, and our focus is on these. So, why do we care about semantic 3D city models? Because they can enable applications such as urban planning, navigation, and large scale simulations. So, here we can see some images. Image 1 is the input, which is raw point cloud data. Images 2 and 3 are added to provide more contextual cues about what we are dealing with here. The raw data is essentially tabular, consisting of coordinates and other scalar fields. But in this pipeline, we are not using any additional metadata such as color or intensity or anything like that. And in the fourth image, we can see the reconstructed buildings and roads overlaid on the raw data. And all of these are visualized using Cloud Compare software. Before diving into the methodology, let me highlight some key challenges. First, heterogeneous LiDAR modalities. Mobile LiDAR or MLS provides dense facade and vertical information, which is very useful for capturing walls and edges. However, in practice, MLS datasets like Paris Lille often cover only partial views of the buildings, typically the visible facades along the trajectories. On the other hand, airborne LiDAR or ALS provides dense roof coverage over large areas, but it has very sparse vertical information. So while ALS give broader coverage, it introduces ambiguity in structural details like orientation and all. So this means our reconstruction approach need to be robust across both modalities despite their fundamentally different characteristics. Second, LOD1 pose estimation. At LOD 1.0, the buildings are represented as simple cuboids. So essentially, a rectangular footprint extruded to a certain height. But estimating the correct horizontal orientation of that footprint is not a straightforward process, especially when vertical cues are weak, as in ALS data. And more generally, we deal with limited ground truth data at scale, along with noisy and incomplete point clouds caused by sensor noise and other scanning artifacts. So all of these factors directly impact the reconstruction quality. Now about HybriDTVis. Our contributions include a semi-automated road reconstruction method using geometry-aware junction detection and constraint mesh generation without needing RGB or trajectory data. Then LOD1 building reconstruction across both MLS and ALS using geometry-driven pose estimation. And a lightweight web-based hybrid rendering tool combining Poetry Core and 3.js. One goal we had from the beginning was to check whether roads and buildings can be reconstructed in a mutually informed way. And while going through existing work, one major gap we identified and we address here is the lack of unified pipelines from raw point clouds all the way to reconstruction and visualization. So the state of the art we have now mainly focuses on separate workflows. This brings us to our proposed pipeline, HybriDTVis. We start with raw point clouds, which first go through panoptic segmentation, giving us semantically labeled and instance-aware data. Next is the road reconstruction module, which involves topology detection, junction-aware splitting, and road segment generation. Since we don't rely on trajectory or RGB data, we instead adopt a geometry-driven approach where the road network is decomposed into simpler segments, then processed iteratively, then merged to form consistent road surfaces. These reconstructed road surfaces could then act as structural prior for the next stage, which is LOD 1.0 building reconstruction. This module includes ground alignment, post estimation, and keyboard generation. Finally, all these outputs are integrated into a hybrid rendering system where we visualize both original point clouds and the reconstructed road and building geometry together. Let's start with the first stage, which is panoptic segmentation. So city scale reconstruction require both semantic and instance level understanding, together referred to as panoptic segmentation. For semantic segmentation, we use established models such as KP-Gun and Randall to classify points as buildings and roads. For datasets without instance labels such as AHN3, which is the Netherlands dataset, we apply connected components analysis to separate out individual building instances with an octree level of 12 and a minimum component size of 200 points. For road extraction, we rely on semantic segmentation followed by manual refinement, since high precision is critical due to the complex topology of the road networks. And in the case of HN3, we manually annotated the road class by cross-referencing it with the map data. Now, moving into the core methodology, we'll start with road reconstruction. Road networks have complex structures including intersections, branching, and irregular connectivity. So, reconstructing the entire road network directly, especially without RGB or trajectory data, is quite unreliable. So instead, our approach is to first detect the junction points, then partition the network into simpler linear segments, and then finally process each segments independently. So we explored two strategies for detecting junctions. The first is a density-based approach based on the intuition that junction regions tend to have higher local point density. So we analyze the point cloud density over a local radial neighborhood over each point and apply a threshold to identify potential junctions. However, in practice, this approach did not perform well because point density is strongly influenced by scanning geometry and variations in road width and all. So this led to a significant number of false positives. The second strategy which we prefer is a geometry aware local PCA. For each point, we compute the covariance matrix over its local neighborhood, giving us three eigenvalues, lambda, 1, 2, and 3. In a straight road segment, the structure is linear, so lambda 1 dominates. At a junction, the structure becomes more planar or spherical, so all three eigenvalues are comparable. But since we are dealing with roads, which can be treated as a 2D entity for topology detection, we define a junction scalar as Sj, which is lambda 2 divided by lambda 1. When Sj is near 0, we are on a linear segment. When it is closer to 1, we are at a junction. So this provides a stable geometry driven indicator of road topology. The comparison on the slide clearly shows that the PCA based detection is significantly cleaner than the density based detection. Once the junctions are detected, we move to junction aware splitting mechanism, which is described in the paper as algorithm 1, and you can see it here as well. But I won't be covering the algorithm in detail due to time constraints, but the intuition behind it is quite simple. We separate the road segments using extracted junction centers from the previous step. Once the linear segments are obtained, we can attach the corresponding junction regions back to them. This gives us a set of individual road segments with junction geometry attached, which can then be used for consistent surface reconstruction and merging. For surface generation, we use concave hulls to approximate the boundaries. Then we apply constrained Delaunay triangulation using reduced interior points from the road point cloud. Finally, the segments are merged and cleaned using PyVista to form watertight road meshes. So here we can see the results. So the first figure on top is the before and after fusion, and below we can see the effect of different reduction ratios. So higher reduction leads to cleaner meshes with 95% giving the best balance. And apart from this, we also tried a Voronoi diagram based centerline extraction and extrusion method for road reconstruction, but it had several limitations, so we are sticking with the constrained mesh generation approach. Yeah. Moving to the building reconstruction module. So we follow 3 steps: ground alignment, post estimation, and cuboid generation. Ground alignment is very important for ALS data. Without it, the cuboid end up floating or vertically misaligned. The fix is pretty much straightforward. We estimate the local ground elevation by analyzing a neighborhood around each building's centroid. We take the mean Z value from this radial neighborhood. This provides a consistent vertical reference. So we can see the before and after results on the right side. Yeah. And for post estimation, we evaluated nearly 5 techniques. The one I'm presenting here is the method we prefer for large scale reconstruction, a contour based analysis with multi-line ransack. So we extract the ridge candidate from upper percentile of the building heights and uses a voting mechanism to determine the dominant orientation. So this method performs well across both ALS and MLS datasets, especially for buildings with gabled and hipped roofs. But we are using a fallback as minimum area rectangle whenever needed. The image here compares some of the previous methods. The last one is a ransack based method which performs well with gable roofs, but tend to have some bias towards certain directions with, because of the scanning artifacts from the ALS dataset itself. Finally, we generate LOD1 cuboids by extruding the oriented footprints to the building height. So this gives simple but consistent building representation aligned with the data. So here you can see the raw point cloud data, the segmented building class, and the reconstructed building and road meshes overlay. And now the final stage, hybrid rendering and visualization. For rendering, we implement a web-based hybrid system that supports both point clouds and reconstructed geometry. So we use a combination of Pottery Core and 3.js. The Pottery Core handles efficient hierarchical octree-based point cloud streaming, while 3.js manages the full scene including camera, orbit controls, lighting, shadow maps, skydome, and the WebGL renderer. The reconstructed geometry is loaded as standard 3.js mesh objects, and everything is abstracted into dedicated reusable classes for maintainability. And we can see HN3 visualization here, and at the top left we could see 3 small panels are added to monitor the FPS and resource utilization as well. We used HN3 and NPM3D or Paris Lille 3D datasets for our experiments. For HN3, which is a Netherlands dataset, we selected 3 tiles covering diverse regions including industrial and countryside. So these tiles contain roughly 300 to 600 buildings. For Paris Lille, we used 50 class version of the dataset as it provides instance level segmentation. And at the hardware level, we used an AMD Ryzen 9 processor with 128 GB RAM, coupled with an RTX 4080 Super GPU with 16 GB VRAM. And similar to the HN results, we can observe consistent reconstruction performance on Paris Lille dataset as well. And this is a demo video of HybriDTVis rendering system on HN3 dataset. You can see the reconstructed building cuboids and road surfaces rendered alongside the raw point cloud, giving a clear view of the integrated hybrid scene. So we have already seen the qualitative results. Now on the quantitative side, we use RMSXY, which is an error metric. So lower values indicate better performance. But please note that this is a proxy metric for planimetric accuracy, since standard higher level of detail evaluation metrics such as completeness, surface overlap and all are not applicable at this level of abstraction, and we evaluate this only on the HN3 dataset, which is ALS, as the MLS data is quite incomplete and the centroids often fall within the vertical walls. So as shown in the table, ransack voting achieves the lowest RMSXY across all three tiles, indicating the tightest planimetric consistency. However, it is also the most sensitive to scanning artifacts, which is why we prefer the contour based multi-line ransack method. Sharing our key findings. So we have implemented 5 LOD 1.0 reconstruction techniques, and our findings show that the reconstruction strategies are strongly influenced by the LiDAR modality, and ground alignment is kind of essential for ALS. Without it, the reconstruction fails miserably. Road-based priors are useful but not universally reliable. We also observe challenges as segmentation errors, scanning artifacts, and lack of standardized evaluation metrics for LOD 1.0. To summarize, HybriDTVis contributes 3 things: a semi-automated road reconstruction method using geometry-aware junction detection and constrained mesh generation without needing trajectory or RGB data. LOD 1.0 building reconstruction across both MLS and ALS using geometry-driven post-estimation, and a lightweight web-based hybrid rendering tool combining Portree Core and 3.js. For the future work, we plan to replace the connected component analysis with robust instance or panoptic segmentation technique for better city scale building separation, and to extend the pipeline toward LOD 1.2 with more detailed footprint geometry. Yeah. So thank you for your attention. HybriDTVis is available as an open source implementation, including reconstruction pipeline and hybrid visualization framework. Questions and discussions are welcome. Thank you.